Good morning, students, and welcome to the chemistry lecture. And now we revise the subpoints that you have studied in the kinetic theory of gases. At first, you have studied the important laws of ideal gases or perfect gases. And that laws are Boyle's law, Charles' law, Avogadro's law. Okay, then you have studied the ideal gases, the gases who obeys the ideal gas laws at all conditions of temperature and pressure. And all of you know the gas molecules moving in a constant random motion. Their collisions are elastic. There is no attraction or repulsion with the container. These are the characteristics of ideal gases. Then you have studied the distinguishing characters of ideal gases and non-ideal gases, and the two important assumptions of kinetic theory, they do not hold good for the real gases, and that two assumptions are the volume occupied by gas molecule is negligible as compared to the total volume occupied by the gas molecules in case of ideal gases, but it is not true in case of real gases due to the size of the uh, gas molecules. And the another assumption, that is the force of attraction among the molecules are negligible, or the force of attraction is zero in case of ideal gases, and it is not true in case of real gases. That means the force of attraction are not negligible at all temperatures and pressures, and ideal gases obeys ideal gas equation, that is the Pv equal to nRT, and real gases obeys the van der Waals equation that we have derived, and that equation is P plus A into n square upon V square into V minus Nb, it is equal to nRT, where N is the number of moles of gas. Then this is the nature of the curve, that means the pressure versus volume. As pressure increases, the volume decreases. You have seen according to the Boyle's law, the PV values are constant. Then the deviations of real gases from the Boyle's law. With the help of this diagram, you have studied the deviations of real gases. Then these are the two reasons for the real gases. They deviate from ideal behavior. Here, the actual volume of the molecule is negligible in comparison with the total volume of the gas, and it is not true in case of real gases. And there is no force of attraction between the gas particles. These two assumptions become wrong at high temperature and at high pressure and low temperature condition. Remember well, these two assumptions become wrong at high pressure and low temperature condition. Then you have studied the compressibility factor. It gives the deviations of ideal gas, okay, and a real gas. Here the extent of deviation from ideal behavior, it is given by the compressibility factor. Then these are the deviations. Okay, this is the van der Waals equation. Then we have seen the effect of pressure and temperature. We have you have studied the relationship between van der Waals constant and critical constants. Then this is the pressure correction term. Here it is, you have studied the exceptional behavior of hydrogen and helium. Then you have studied the Andrews isotherms. Okay. And here, Pc equal to A upon 27 B square, while Tc, that means critical temperature, it is equal to 8A upon 27 RB, and Vc, it is equal to 3B, that you have studied here, the relation between critical constants and van der Waals constant. Here critical temperature Tc equal to 8A upon 27 RB. Pc critical pressure, it is equal to A upon 27 B square, and the critical volume Vc, it is equal to 3B, while the boil temperature we have as A upon RB. You have studied it. And for the last lecture, I have explained you the most probable velocity, average velocity, and RMS velocity. You know, the assumptions of kinetic theory of gases, the that assumption is all the molecules they travel with the same speed, but it is not true. Okay, here the molecules are always in a random motion. They collide with each other and walls of the container, and while colliding, the molecule's energy, it will be lost, or the one molecule, it gives its energy to another, and their energy, it may either increases or decreases, and depending on that, the distribution of their velocities, it is given by the Maxwell-Boltzmann distribution law, and the average speed or average velocity, it is given by 8 kt upon pi m. Then average speed, it is equal to 3 kt upon m, and 3 square root of 3 kt upon m, it gives the root mean square speed or root mean square velocity. So the distribution of velocities, it is explained with the Maxwell-Boltzmann relation, and it is given by this equation in your textbook. Here dEnc by n, it is equal to 4 pi in bracket m upon 2 pi RT raised to 3 by 2 into e raised to minus mc square upon 2 RT into c square dc. As the molecules collide with each other, they loses their energy as well as velocity, and a fraction of molecules, they have the same velocity, and it is given by this Maxwell-Boltzmann distribution law. Here dNc by n, it is equal to 4 pi m upon 2 pi RT raised to 3 by 2 into e raised to mc square upon 2 RT into c square dc, where dNc is the number of molecules having velocities between c plus dc. This capital N is the total number of molecules. This m is the molecular mass, and T is the absolute temperature. This equation is called as Maxwell's law of distribution of velocity, and the ratio dnc by n gives the fraction of total number of molecules having velocities between c and c plus dc. Here, Maxwell plotted such fractions against velocity possessed by the molecules. The curve so obtained explains the silent features of the Maxwell distribution velocities. Here, that means if we plot the graph of fraction of molecules versus molecular velocity, we have this type of graph. This is the curve for 600 temperature, and this is the curve for 300 temperature. And here the tip of the curve, it gives the most probable velocity as well as the average velocity, and at this we have the root mean square velocity. That means few molecules have the average velocity and most probable velocity. Okay, here the distribution of molecular velocities of nitrogen gas at 300 Kelvin temperature and 600 Kelvin temperature, it is shown in this figure. A very small fraction of molecules has either very low velocity or close to very high velocity. Then the average velocity represented by the peak of the curve. The velocity is called as most probable velocity, which may be defined as the velocity possessed by the largest fraction of molecules corresponding to the higher point on the curve. At higher temperature, the whole curve shifts to the right. That is the dotted curve which is shown in the diagram. This shows that at higher temperature, more molecules have higher velocities and fewer molecules have lower velocities. And then the next point, that is different kinds of velocities. In the study of kinetic theory of gases, we observed three different kinds of molecular velocities, namely average velocity, denoted by letter V, root mean square velocity, RMS, it is denoted by letter nu, and the most probable velocity, it is denoted by V at the base MP, that is most probable velocity, which can be discussed as below. Here the average velocity. What is meant by average velocity? Suppose there are n molecules. We have n molecules of a gas having individual velocities v1, v2, v3 up to vn. Then the ordinary average velocity is the arithmetic mean of the various velocities of the molecules, as v bar, it is equal to v1 plus v2 plus v3 plus plus Vn divided by n. That means here we have sum of all the velocities of all the molecules and divided by the number of molecules. It gives the average velocity, and putting bar over V, we get the average velocity, or average velocity, it is denoted by V bar. From Maxwell equation, it has been shown that the average velocity V average is given by the expression here square root of 8RT upon pi m, and this ratio becomes here 8 divided by the value of pi, that is 3.142, we get 2.55 RT upon m, and substituting the values of R, T and pi and m. In this expression, the average value can be calculated. Okay. By using this equation, we can calculate the average velocity. That means simply multiplying 2.55 by R and T and molar mass, we can get the average velocity. Then we will see the root mean square velocity. If Phi1, Phi2, Phi3, Pn are the velocities of n molecules in a gas, then mean of the squares, that is Phi square, of all the velocities is given by here mu square, it is equal to Phi1 square plus Phi2 square plus Phi3 square plus Phi n square divided by n, and taking the square root, we get mu equal to square root of Phi1 square plus Phi2 square plus Phi3 square plus dot dot plus Pn square divided by n, and by using this formula we can find the root mean square velocity. That is, mu is the root mean square velocity or RMS velocity. It is generally denoted by letter mu. The RMS velocity mu at any given temperature can be calculated from the kinetic gas equation as follows. We have the kinetic gas equation as P phi, it is equal to 1 by 3 m n u square, and from this equation we have u square, it is equal to 3 p phi by m into n, and for one molecule, 1 mole of gas, here we have p phi equal to RT. Therefore we replace p phi by RT, and hence u square, it is equal to 3RT by Mn, it is equal to 3RT by M, where M is the molar mass, and nu, it is equal to 3RT by M. By substituting the values of R, T and M, the value of RMS velocity can be determined. The RMS velocity is superior to the average velocity. With the help of RMS velocity, the total kinetic energy of gas molecules can be calculated. And then the most probable velocity. Here, the most probable velocity is possessed by the largest number of molecules in a gas. According to Maxwell's calculation, the most probable velocity is given by the expression here. Most probable velocity, it is equal to square root of 2RT by m. Substituting the values of R, T and m in this expression, the most probable velocity can be calculated. Okay, then the relation between average, most probable and RMS velocities. Here, average velocity, it is equal to 0.9213 into RMS velocity, and most probable velocity, it is equal to 0.8165 into RMS velocity. Okay, remember these two equations and prepare this chapter well, and next time you will learn the kinetics or the study of rate of reactions. Thank you, and in the next week you will have to attempt a quiz on this chapter, kinetic theory of gases. So prepare well and solve all the problems that are included in this chapter. Those problems they are given for the uh, your practice. Prepare all these problems so that you can understand the theory well with the help of formulas that are included in this chapter. And if you have any type of uh, difficulty in the understanding, you may ask me so I can solve your difficulties. Thank you. Thanks for your patient listening.